All right, let's look at some practice problems. In this first example, we have we have y and its derivatives up to the third derivative, and we have u and its derivatives up to the fourth derivative. This system is not causal. Why is this system not causal? Well, it turns out the reason this system is not causal is because the input is differentiated more times than the system output. And that actually is what determines what makes it causal or not. If we were to take the transfer function of this system, we would get a system whose numerator polynomial is of order greater than the denominator polynomial. And so one way to see for a transfer function if a system is causal is whether the numerator is of order greater than, equal to, or less than the denominator. If the numerator of a transfer function is greater than the denominator, the system is not causal. If the numerator of a transfer function is equal to the denominator, the system is said to be proper, and it is causal. If the transfer function numerator is less than degree of the denominator, the system is said to be strictly proper. All right, those are some terms. All right, let's take the same system, except now we dropped off the fourth derivative term, and we can go through and show that this differential equation can be put into this observability canonical form this way, just by plugging in and using the formula. I can also choose the controllable canonical form and just again plug the numbers in, and this is what I get when I do that. So it's fairly straightforward. You just plug the numbers in and you're good. You're good to go. Now let's take a look at an example of Gilbert's method of going from a transfer function to a state model. So this is actually going from a differential equation to a state model, but I could also have gone through a transfer function and gone to the state model as well. Okay, so this is my transfer function I want to find a state model for. So first we take the high frequency gain, the limit as s goes to infinity h of s, and when I do that, this is what I get. Okay, so notice this is second order over second order, first order over first order, zeroth order over first order over first order, first order over first order, second order over second order, zeroth order over second order, and zero. So when I take the limit as s goes to infinity in this, anytime I have something like this, where the order of the numerator is less than the order of the denominator, that will go to 0. Okay, so this term goes to 0, that term goes to 0. Okay, and so you can see how that appears here. These two terms were already zeros. Okay, whenever we have the same degree of polynomial, we look at the coefficients, and actually the coefficient of the highest power in both numerator and denominator. And that's what happens when we get the limit. That's using L'Hopital's rule. So we get this here, we get -1 here, we get 1 here, 1 here. Again, the coefficients are 1 here. That's a monic polynomial. Usually when we write a transfer function, we write it as a monic polynomial. That is, the leading coefficients of s are 1. In this case, I get a 2 when I take the limit as s goes to infinity. So this is my d. Okay, so that's my d term. And now I define g to be h minus d. So when I do this now, all of the transfer function elements within the transfer function matrix will be strictly proper. Okay, so here all of the elements are proper or strictly proper. That is, the order of the denominator is greater than or equal to the order of the numerator in every case. Okay, so in this case, we end up with things that are only strictly proper. So it turns out you need to have things strictly proper when you do a partial fraction expansion. Okay, so we do a partial fraction expansion of every term in the matrix. So this becomes that. So notice in a lot of these cases, like these, I don't have to change anything because it's already expanded. But this term and this term I needed to expand. Okay, so that's the partial fraction expansions. Now, if I look at the poles, I have a pole at s minus 1, I have a pole at s plus 1, I have a pole at s, and a pole at s minus 2. So I have 4 different pole values here, and they're all simple poles. Okay, so if I were to find, for example, the matrix, so the matrix that involves the partial fraction expansion matrix that involves 1 over s, notice that 1 over s only appears in these 2 terms. It's 0 everywhere else. So when I do the partial fraction expansion, I get those 2 terms, 0 everyone else associated with 1 over s. I do the same things with 1 over s minus 1, 1 over s plus 1, 1 over s minus 2. So these are the matrices that I get. So notice we get a lot of zeros coming out because most of the terms do not depend upon that pole. So I now have 1, 2, 3, 4 matrices, the RIs, R1, R2, R3, and R4. Notice that this matrix is of rank 1. That is, there's only one linearly independent row or column, right? So I have one independent row. All the others are zeros. In this case, I have one independent column. Here, notice I have 2 independent rows or 2 independent columns. So this has rank 2. This has 1 independent column. So these 3, the R's, the RIs, are 1. This has an RI of 2. Okay, so we now factor these according to their LR factorizations, and we can go through and show that these 4 matrices have these factorizations. Okay, this matrix can be factored this way. This matrix can be factored this way. Notice that the rank of this matrix is 2. The rank of this matrix is also 2. This matrix can be factored this way, and this matrix can be factored this way. So that is how I get my B's and C's. My A matrix is again the diagonal of the poles. So in this case, we have a pole at 0, a pole at positive 1, a pole at minus 1, and a pole at positive 2. Actually, I'm going to get 2 minus 1s because remember the rank was 2. That is, R3 was 2. And so this is the form that we get. To form the overall B matrix, so this is how we form the overall A matrix. It's a diagonal matrix. To form the overall B matrix, I stack the B matrices. So notice I have, this is a row, a row. This is a 2 by 3 matrix, and then a row. I then stack the C matrices side by side. So again, remember the rank here was 2, and this becomes my C matrix, and the D we've already computed. So that is an example using Gilbert's realization. So now, given a state model like this, how would we find the transfer function? How would we find the transfer function? Well, we can use the formula. Transfer function is D plus C SI minus A inverse B. So here's D, C, this is SI minus A, inverse B. So when I multiply all this out and take a symbolic matrix inverse, multiply it all out, I get this function. Okay, so in order to go from a state model to a transfer function, I need to do something like a symbolic matrix inverse. Now in MATLAB, if you use the command state space ss to tf, state space to transfer function, it will give you, it does not actually do a symbolic matrix inverse. It knows how to compute it by an alternate means. So notice the poles are always the roots, or rather the eigenvalues of the A matrix, and so or the characteristic polynomial of the A matrix. So there's the characteristic polynomial of the A matrix. And so it's the numerator that's the tricky part to find in computing all of this. So symbolic matrix inverse, which we can do in MATLAB. Okay, so I'll show you that now. Let's take a look at that now. Okay, so here's the system. Okay, in this case, A is given by the matrix minus 2, 3, 0, minus 3, minus 2, 0, 0, 0, minus 7. B is given by 0, 1, pi. So notice it gave me a numerical value for pi. Y is equal to 1, 0, minus 5. I'm sorry, that should be C. And D is equal to minus 3. Okay, so we've got A, B, C, and D. I can, using symbolics, I can do sims S. It takes a while to do that. And now I can define G to be equal to D plus C divided by S times the identity minus A times B. So this slash here basically tells MATLAB that I want this next matrix to be inverted. So we can go through and do that calculation, and boom, it spits it out. So notice that even though when I entered it as pi and it gave me a numerical value, when we did it symbolically, it recognized pi and said, oh, that's pi. I don't need to use the numeric value, I can use the actual value. And this is what we get. We can put it all over a common denominator by saying factor G. And so that's what we get. So there's s plus 7, s squared plus 4s plus 13. And then there's all that other stuff that includes pi in it. So we can do this symbolically. Okay, well, let's go back to our slides. Here I have a transfer function matrix, and I want to get a state model for this. And as we've seen, there's a direct method, or rather there is a direct method for getting a state model, and so this is the direct method. Okay, or we can use Gilbert's realization, and this is how we would obtain it using Gilbert's realization. We've already gone through and done an example using Gilbert's realization. So the direct method I haven't shown you, but there are other methods. And in this case, you can see it gives you a matrix, or rather a state model that is much bigger than this. So this is of minimal order, and so that's what we have. So this is system models and working with state realizations.